Thank you and good morning. I apologize for not being able to make it in person. I wish I could be there and join in the discussions. But I'm Suman Banerjee from UW Madison. It's a pleasure for me to be part of this team and be leading the networking thrust of Athena. So before I proceed, I should introduce an excellent reporter of team members here from across four institutions, uh, including Duke, Michigan, Yale, and Wisconsin. And we hope to accomplish some important goals in designing sort of the next generation of mobile networks. At a high level, very, very high level, 10,000 feet level, our intended outcomes is to allow us to design mobile networks that learn and learn efficiently. We wanted to have explainable configurations, which will leverage the emerging AI techniques. And all of our developments we expect to be deploying in form of trials with various partners and on power platforms. So we look forward to some of these outcomes in the coming years. So if all of you perhaps in this room know that designing a mobile network is a challenge. The old world had a certain way of doing this. The old world I call is what I call the 3G and the 4G networks, where signal processing would happen at the RRUs, radio resource units. There is connectivity back to the core networks and the cloud. And to quote Bob Dylan, the times they are changing. There are many new developments that has emerged over the last decade. We have seen increased softwareization with emergence of SDNs and Cloud RAN. We have seen the emergence of very high frequency wireless communication technologies as we move towards the future generations with the opportunities around terahertz communication. They come with some challenges like high fragility. These links can break quite quickly and can have very disruptive effects also. And there is a huge explosion in the state space on configuring wireless environments, wireless nodes. And then the big opportunity is around huge amounts of compute resources that are available at different parts of the network and AI capabilities that can be placed on this compute. So to take advantage of that, I think we will move to a new world where we now in this institute, I think we can think of designing a mobile network to be a computational problem. It is not just figuring out how to route traffic, route packets, route signals, but we can essentially have the opportunity of doing signal and packet processing in edge or cloud data centers, and that can completely transform how we do things. So we will address a number of challenges in the networking thrust, but broadly in the whole institute. These are the terms may seem the same as maybe previous iterations of network design, but I think the scale of some of these activities are pretty significant. So when we talk about challenges in adaptability, when we are going from gigahertz to terahertz, it's a completely new new kinds of issues we have to deal with when we are going from gigabit to terabit speeds, or when we are trying to reduce latencies from a few milliseconds to sub-millisecond latencies that are going to be demanded by emerging applications. We will be looking at significant efficiencies that are necessary for network configuration and resource allocation with much more tighter timing constraints. We need greater programmability to support flexible distribution of AI compute across cloud and edge resources. Improve trustworthiness because we are also increasing the attack surface through which these networks can be more vulnerable. And then scalability because we all know of the explosion of number of devices and the number of standards that continue to emerge. So the networking thrust, we kind of really touch upon all parts of the end-to-end system. We have the wireless networking part, we have edge systems, we have core networking, and we have cloud, and we have connectivity across all of them. So we touch upon all of these. I will highlight some of interesting problems that we have already started thinking of. In fact, we had our very fun retreat yesterday, and some of the content that I'm going to present is actually come out of discussions from yesterday. It's not old material that we're presenting from previous iterations of this. So I want to spread a little bit of this discussion into two parts. We want to talk about AI-supported network systems and then network support for AI systems. So I think that's kind of a nice theme which leverages the synergy that this team will have across the different thrusts. Of course, there are other synergies too, but these two are the ones I want to highlight. So one of the challenges we want to address is as wireless environments continue to be highly dynamic, how can we quickly learn about what's happening in the environment and adapt? And if you look at these very highly fragile and high capacity links, you can learn parameters of the link in one time. But once it changes, learning the new parameters of a new distribution of channel conditions usually can be time consuming if you apply the same kind of AI techniques. So we would love to leverage approaches such as domain adaptation, where using a few samples in the new domain, we can learn the properties very quickly, because that would be necessary in highly mobile and highly dynamic scenarios of that nature. A related example is radio nodes that can learn their physical world and adapt. So typically, if you think of these radio nodes, they try to algorithmically predict what their adaptation should be, and then they slowly evolve. However, if you imagine a road that goes by some base stations, you will observe that cars come from one direction and exit on the other direction, and they happen repeatedly. And if we can learn these patterns, if we can learn what an environment looks like and optimize for certain cases, it will lead to much more efficient learning. So there are some great opportunities in doing so, where we can learn about the environment, learn about the characteristics of the environment, the physical world, not just the wireless world. And that will give us some great opportunities for greater optimization. Uh, Another similar example we have is in the domain of broadly spectrum sensing, which is a very, very important problem as spectrum policy gets more flexible. You know, there are people in the audience who have been pioneers in this field, Victor Ball and others in Microsoft, who led very significant changes to spectrum policy in the FCC. So they all know that improved spectrum sensing is critical. But spectrum sensing is a hard problem because of the scale of compute, storage, and networking needed. Imagine you're trying to sense activities everywhere. So this is very hard. And if you were asked a query, tell me what anomalous thing happened in say the LTE band between 10 and 12 noon on November 18th in Durham, North Carolina. It's not easy to answer, and so you have to figure out appropriate methods to address this problem. So we're going to look at some specific techniques, including out of distribution techniques, and we're going to also explore topics around what we call application specific sensing. So if I knew why I am sensing, I may apply some specific methods of analyzing data at the edge, applying compression techniques, because you cannot take and transport all spectrum data to the cloud. That is going to not scale. So if I knew how I'll use this data, maybe I'll compress things in a certain way, versus if I was looking at a different application, I may compress it in a different way. Those things can give us significant benefits. And then, of course, we would need help from our colleagues in AI to understand how to split various machine learning algorithms between the edge and cloud. So there are some great opportunities in these spaces that we can approach. Now, going towards network-supported AI systems, so there is lots of machine learning problems, ML applications that are out there that I think networking can help. So just to take an example, let's say there are multiple distributed clients that want to jointly learn an objective. Commonly, there are techniques such as federated learning that are used to approach them, and they cannot share data with each other. That's why kind of you have to do this. So how do you do sharing? What do you share, and how do you do sharing? And the challenge is that data is coming continuously, and not if you want to train, you cannot train it on one set of data and then create a model and say, okay, we are done, because new data continuously is arriving, and we have to decide which of the existing data and the prior data should we use to create the model, to evolve the model, and how should we share this data. So there is very interesting problems of how new data arrival influences our decision making. There are traditional problems in networking on how to cache content. This is caching, but in a completely different context. And there are some opportunities to do that, which also needs to take data privacy into account. A broader version of the same problem could be sensing in our real world, in our home environments. So if you followed a lot of activities in our day-to-day lives, there are numerous technologies that are trying to track and understand how people are operating, what they're doing, so that they can customize actions in their homes. There are efforts in doing RF sensing, which can tell a person's heart rate just using RF signals, or detecting sleep apnea problems. So there's lots of sensing that's happening. Now, the sensors which are sitting in homes are very small devices. And then, of course, you want to run very sophisticated signal processing and other ML techniques on top of it. Now, again, like the spectrum sensing problem, you cannot offload all this data to the cloud. So you have to do some distributed processing between cloud, edge, and even the sensors. And then you have a network which is dynamic, which is highly variable, and it is not always possible to have a high bandwidth network from everywhere. So if you're trying to do sensing in the home, and people are also using their networks to do other things, this sense data cannot just be shipped through their network uplinks, because that is going to interfere with what the home users are doing. So there is very interesting opportunities of co-designing AI tasks with networking protocols and storage and compute. So I think these are some of the very big challenges that we will hope to undertake in the coming years, and with various collaborations that we have in place. So coming back, we have these four sort of areas of broadly networking that we want to touch upon. I think I am at the conclusion of the broad overview, but we would like to throw some spotlights on a couple of research directions, specific problems that a couple of our colleagues are going to work on in the initial years. So Wenjun Hu from Yale and Tingjun Chen from Duke are going to talk about some specific aspects in wireless networking and core networking research in the next maybe 20 minutes. So with that, I will stop and hand over to the spotlights. Thank you.